Good morning. This is your stat sensei, Mr. Spensei, and this is classwork, and this is just going to be the confidence interval part of the classwork, and then we will follow it up by doing the hypothesis test. So, lead found in some paints is a neurotoxin that can be especially harmful to the developing brain and nervous system of children. Children frequently put their hands in their mouth after touching painted surfaces, and this is the most common type of exposure to lead. In Flint, Michigan, many have alleged that the amount of lead exposure is significantly higher outside than inside. That might be important because we have a direction. So they're saying outside might be higher than inside, and have recommended that daycare center no longer allow children to play outside due to the amount of exposure to lead. The city of Flint has commissioned a study to explore this claim and randomly selected 9 children. That's going to be important. So we randomly selected 9 children from over 35,000. That's probably important as well in urban daycare centers. To conduct a study, the hands of the children were wiped clean. They were then allowed to play outside for 1 hour, after which the amount of lead in micrograms on each hand's dominant hand was recorded. The children's hands were cleaned again, and they were permitted to play indoors for an hour. After the 1 hour of indoor play time, the amount of lead on each dominant hand was measured. The data for the amount in mcgs of lead on each dominant hand are shown in the table below. All right, so we have all the data entered into, we have all the data for outside and inside. So let's go ahead and input that into our calculator. So I've done that. And then I have these figures. These are not for our test. All right, these are not for our test. These are check values. So let's go stat calc one variable statistics, L1. And this way we can check to see, hey, 17.55 and a standard deviation of the outside is this. That's great. We go stat calc 1 var and change it to L2. And we get 14.55 is the sample mean for that with a standard deviation of here. But what we're really interested in is they were tested twice. They were tested once on their dominant hand playing outside, then they were tested again indoors. And so we went outside minus inside. So I'm going to go ahead and write that down because that's going to be important. Outside minus inside. And you can see that 15 minus 16 is -1. 25 minus 15 is 10. All right, so we can see that they were subtracted outside minus inside. But I can go to the calculator and I can update that by going up to the top of L3 and go second 1, the blue button -1, and the blue button and the number 2, and it populates it. All right, let's go ahead and do that stat calc 1 var stats again, but let's do it for column L3. And I end up with the X bar, and this is really the X bar D equaling 3. And I end up with an SD, and I don't have enough room, but so we'll just only take it to a couple places for right now, a 4.85. So these are the values we're interested in. And I'm going to go ahead and slip down and get a little bit ahead of myself and record those. So XD is 3, SD is 4.8541, 4.8541. We'll come back to that in a bit. It says construct a 95% confidence interval for the data. Well, the first thing we need to do is write our parameter. So let mu d equal the true population. And since we're doing paired, it's going to be mean of the differences in amount of lead. And it's really amount of lead on dominant hand, but we'll just go in amount of lead. And then we're going to go, what order did we go in? We went outside minus inside. All right. And we think the outside is going to be bigger. And I'm just going to we're going to say the outside is going to be bigger than the inside. This is going to be smaller. Oh, conditions. So our first condition, well, random sample. And remember, when it's paired, we're not looking at how many points we entered. We're looking at how many pairs of points. So in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's what they said. They said we had 9 children. So that random sample of 9, and that was given. The next thing, the differences are independent, which they will be if it's a random sample. Differences are independent. Three, the next thing is the less than 10%. Well, our sample size is 9, so n equals 9. 9 times 10 equals 90, and that's very clearly less than the 35,000. Is less than 35,000. So that's taken care of. Finally, we need the normality. So our sample size is not large enough. So hopefully they told us this was normal somewhere. Um, well, I'm not saying that it's normal, but we're going to assume that it is, and I'm going to have to add that to this. All right, so the distribution is normal. Um, Differences are normal, and it's going to have to be given. I'm going to have to add that in. I apologize that it's not in the video, but I'm not going to go remake it. Differences are normal, so we just added that in because it needs to be there because our sample size isn't large enough. Okay, we need our equation, which is just x bar d plus or minus t star sd divided by the square root of n. They wanted us to run a 95% interval, so that's 0.95. And they said that we had 9 children, so that's our sample size. So the first thing we need to do is calculate our uh, t star. And to do that, we're going to have to go inverse t, and it's going to ask us for the area. Well, the area is going to be 1 minus our confidence level of 0.95 divided by 2, and it's going to ask us for our degrees of freedom, which are 9 minus 1, or 8. So let's go to our calculator and run that. So second vars, inverse t, parenthesis 1 minus 0.95, close parenthesis, divided by 2, degrees of freedom, 9 minus 1. And we get 2.3060. Please make it positive. 2.3060. And then we're going to plug in. So in this case, we have 3 plus or minus 2.3060 times 4.8541 over the square root of 9. So here we go. Stat test. This is going to be number 8 for a t interval. We have data. The data we're interested in are in L3, so second 3. And our confidence level is 0.95. And we chose L3 because that's where we put the differences. And we end up getting negative 0.7312. Oops. Negative 0.7312 to 6.7312. Now, it's important to note that 0 is contained. And because 0 is contained, we can't say at 95% confidence that there is a difference. All right? We definitely have some evidence because we have a difference of 3, but we don't have enough because the interval contains 0. All right. Hold on, and we will get to the and we will head to the hypothesis test in just a moment. All right, we're going to continue on. We just ran the confidence interval. We're going to go ahead and run the hypothesis test. I filled in the data here that we've already talked about. And remember, we went to our calculator. We'd already inputted into L1 and L2. So there's our data entered, and 15 minus 16 is -1, which means we're actually going to go outside minus inside, which is column 1 minus column 2. And we get our data. We can do a stat calc 1 var stats for L3 because that's where the differences are, and that's what we care about. And that's where we get our 3, and we also get a standard deviation of 4.8541. I'm going to go ahead and record this down here because that's important information that we're going to need here in a little bit. So XD is 3, and this is 4.845, excuse me, 8541. All right, 4.8541 for our standard deviation. All right, so the first thing is we need to write our parameter. I just brought it over from our original. Let mu d equals true population mean of the differences in amount of lead outside minus inside. This part right here we don't need. This is just to help us out. We expect the outside to be bigger than the inside, so bigger minus smaller. So our hypothesis, well, the HO is easy. All right, that part's easy. It's always going to be mu d equals 0. But we need to explore this just a bit. So bigger the outside and the inside. Well, we expected the outside to be bigger, and we expect this to be smaller. So take a bigger number, and let's just say we take 15 and we take 10. I just made those numbers up because that's a bigger number. So this means this is going to be shaped that way. So my hypothesis is going to be HO mu D equals 0. HA mu D is greater than 0. Please remember, if we're working with paired data, we're expecting there to be no difference. And if there's no difference, it's going to be 0. In other words, if this is 15, that'd be 15, and 15 minus 15 is 0. That means there's no difference. All right, T equals X bar minus mu S divided by the square root of N. Well, that's the basic T distribution, but we're working with differences, so we need to drop some D's on it, and there we go. All right. The mean of the difference is 0, and we had 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9 children, and we said greater than, so we're shading in that direction. So now we can draw our picture, and we have a mean of 0. We have an X bar of 3, X bar D of 3. And there's our picture. All right, so we need to plug in, and we're going to be looking at the probability that T is greater than 3 minus 0 over 4.8541 divided by the square root of 9. All right, so let's go ahead and run that. Stat test t-test. We need to have data highlighted. Our mean is 0. Our list is L3, so the blue button followed by the number 3. We need to make sure that we have the greater than symbol because that's what we have for our hypothesis. And we're going to ask it to calculate it. And we get a t-value of 1.8540. And so I didn't write a place for that, which is bad. This should have said probability that t is greater than 1.854 gives us a p-value of 0.0504 and an alpha level of 0.10. And you're like, where did you get that? They told us it was a 10% significance level, so that's 0.10. So I need to make them the same length. And 504 is definitely less than 1,000. So our decision is to reject the null. All right. Okay, I appreciate you watching and hope to see you on the next one. Thank you.